Welcome back. In this video, we are going to cover the second section of Chapter 2 about a fundamental concept in topology, the concept of a homeomorphism. The concept of a homeomorphism in topology is similar to the concept of isomorphism in group theory or vector space theory, and is similar to the concept of diffeomorphism in geometry. All these concepts, isomorphism, homeomorphism, diffeomorphism, have something in common. The word morph comes from the Greek, which means form. And homeo means similar, iso means equal. Diffeo actually comes from differentiability, but we are not concerned with that here. So saying that two topological spaces are homeomorphic means that they have a similar form. And saying that two groups are isomorphic means that they have the same form or can be identified, if you like. So they have the same algebraic structure under consideration. For two topological spaces, saying that two spaces are homomorphic means that they can be identified. They have the same topological structure. So we cannot really distinguish between them. And now I'll give first I will give the exact definition, and then I will give very important examples, fundamental examples of homeomorphism. So homeomorphism, as we expect, is a bijection as the concept of isomorphism. So you should have a bijection, but it should conserve the topological structure. And the central idea in topology is the idea of continuity, as we said. So this bijection should be continuous, and its inverse should also be continuous. Okay. Compare this with the notion of isomorphism between two, let us say, vector spaces. There is a little difference, because in the definition of isomorphism between vector spaces, you didn't assume that. So you had a bijection which is linear, but you didn't assume that the inverse is linear, because this was automatic. If a linear map is bijective, then its inverse is automatically bijective. But here, as we shall see now, if a bijection is continuous, it doesn't follow necessarily that its inverse is continuous. So this is why you have to add this assumption. And I'll give examples, actually. Sometimes continuity follows from other assumptions. And we shall give an example in the next chapter. Okay, but in general, it doesn't follow. So this is why you have to assume three things. So if you like continuity and continuity of the inverse, you can refer them together as bicontinuity. So if you like, a homeomorphism is a bicontinuous bijection, if you like. And two spaces are homeomorphic if there exists a homeomorphism between them. Okay. So let us, as usual, give some elementary examples. If you take the cosine function restricted to the interval 0 pi, the closed interval 0 pi, then its image is -1, 1, and it's injective now because we restricted the domain of cosine. If you take the cosine on the whole of R, it's not injective, but if you restrict it to 0 pi, we get an injection. So this is a bijection, and cosine is continuous, as you know from calculus. And the inverse is what we call precisely the arc cosine. And continuity of arc cosine is studied in calculus, so I'm not going to repeat that. So this is a homomorphism. Cosine is a homomorphism between these two closed intervals. And also we have the sine function is a homomorphism between -pi/2 pi/2 into -1, 1, and its inverse is what we call arc sine. Tangent is a homomorphism between -pi/2 pi/2 open into the whole line. And the inverse is what we call arc tangent. So here we have a bijection, it's continuous, the inverse is continuous. Now, there is a little bit surprising geometric interpretation of this example. Because here we understand that these two closed intervals are homomorphic, because they have the same shape. But it's less intuitively clear how a finite interval, -pi/2 pi/2, can be homomorphic to an infinite line. The reason is that what tangent is doing is, if you think of tangent as a geometric transformation, and I always encourage you to think of functions as transformations. What this function is doing something mathematically possible but physically impossible. It's doing an infinite stretching. So imagine taking the open interval minus pi over 2 pi over 2 and stretching it to get the whole line. So this is what, and if you picture the graph of tangent, you will see that its domain is minus pi over 2 pi over 2. It is transformed by some kind of stretching into the whole line. Okay. So, and you'll see actually that any two open intervals are homomorphic between each other. Another trivial example is x cubed. X cubed from R to R is a homomorphism because it's a bijection, it's continuous, and its inverse is given by x to the power 1/3, which is also continuous. Okay, so now we give, as we said, a continuous bijection need not be a homomorphism, and here's an example, a fundamental example actually. Usually we denote the unit circle by capital S1, S to the 1. So it's the one-dimensional sphere, if you like. So, and S2 will denote the two-dimensional sphere, and Sn the n-dimensional sphere. So this is the unit circle of equation x squared plus y squared equal 1. And we consider the map from 0 to pi semi-open into S1, whose components are cosine, sine. Okay. Now, it's very easy to check that this is a bijection. It's injective and surjective. It's easy because you can always solve the system cosine t sine t equal xy, where x squared plus y squared equal to 1 in a unique way. And it's continuous, of course, because each component is continuous. So, however, if you solve precisely the equation cosine t sine t equal xy, so it's a system, x equal cosine t, y equal sine t, you will find the inverse of f. Okay, this is how we usually find f minus 1, by solving the equation f of t equal something. Okay, so if we solve the equation f of t equal xy, we will get that t is r cosine x if y is non-negative, and t equal to pi plus r cosine minus x if y is negative. So this is really something that you learn to do at school. It's not difficult, actually. The y positive corresponds to sine t, or non-negative, corresponds to sine t non-negative, and this corresponds to t between 0 and pi. And the y negative corresponds to the lower half of the circle, so corresponds to sine t negative, or t between pi and 2 pi. Okay, so I'm sure that you are able to solve this system, and when you solve it, you get precisely this formula. And you can rewrite it in a slightly different way, because we can prove that r cosine minus x is pi minus r cosine x. So I can write this as 2 pi minus r cosine x. Okay? Now, if the domain of f is 0 to pi closed at 0, we have a problem, actually, because if we let x and y tends to 1, 0 plus, so y from above, okay? So if we let y tend to 0 from above, we'll get, and x tend to 1, we get r cosine 1. So r cosine 1 is 0, as you know, because cosine 0 is 1. And however, if we let x tend to 1 and from below, so y being negative now, we'll get pi of r cosine minus 1, and r cosine minus 1 is pi, so we get 2 pi, okay? And therefore, this proves that f minus 1 is not continuous at the point 1, 0, which is the point to the right. Okay. However, if you let x tend to minus 1, 0, you'd get the same thing. So this is an example of a continuous bijection, which is not a homomorphism. This is a natural example. And of course, we can invent many others. But this is a fundamental example. However, there is a very important thing. If we restrict f to the open interval 0 to pi, then we will get a homeomorphism. So it's very important, actually, because there is a geometric interpretation of what this function is doing. this very simple function, cosine sine. What is the geometric significance of cosine sine? If you think of as 0 to pi as the object that we have to transform, this f is bending the interval 0 to pi into the circle if we include 0. However, if we exclude the 0, then the image will be S1 without the image of 0, which is 1, 0. So it would be a circle with a point removed, or a punctured circle, if you will. So intuitively, if we bend the open interval 0 to pi into a circle with a point removed, we have still a cut in the circle, so we can go back. However, if we go from 0 to pi semi-closed at 0, we'll get precisely the circle. Okay, so we bend this into a circle. But if you want to go back from the circle to 0 to pi, we'll have to break the circle, and this is why we lose continuity. Okay, so this is very important. There is we denote the two functions by the same symbol f, but they have a slightly different domain. Okay, so maybe we can call this f and this is g. Okay, so f from 0 to pi into S1 is a continuous bijection, but it's not a homomorphism. Whereas g from the open interval 0 to pi into the circle without a point is a homomorphism. Okay. Okay, so we said that. And there is, in contrast, if a bijection between two intervals of R is automatically a homomorphism. Okay, this is something really specific to R. Why? Because a bijection between two intervals of R is either strictly increasing or strictly decreasing. Okay, so we don't have so many choices. So in particular, a continuous bijection between two intervals of R is automatically a homomorphism. Okay, this is one case where continuity of the inverse follows from the assumptions. Okay. And we'll prove that in the exercises. Now, we give more examples of fundamental, of course, importance. So first of all, we saw that the interval 0 pi closed is homomorphic to -1, 1 by the function cosine. But in general, all closed bounded intervals of the form AB are homomorphic between each other. So it's enough to prove that any interval AB with, of course, A strictly less than B, because if A equal B, you get a singleton, and a singleton cannot be homomorphic to an interval. So it's enough to prove that the closed interval AB is homomorphic to the standard interval 0, 1. How do we move from the interval 0 AB into the interval 0, 1, or vice versa? It's very easy to imagine. It's just a translation followed by a homotopy, if you like. So if you consider this map, this is a linear map. So it's given by x minus a over b minus a. So what does it represent geometrically? It's a translation, because I can write this as x over b minus a minus a constant. So it's a translation followed by, or if you like, a homotopy first, or dilatation, or stretching, or contraction, depending on the size of b minus a. So so to go from AB into 0, 1, we first do a stretching and then we do a translation. Okay, this is very easy. Okay, so we can easily check now that this function is a bijection from AB to 0, 1. And by the way, you can easily check here. It's strictly increasing, of course, because A is mapped into 0 and B is mapped into 1. Okay, and we can solve the equation and find the inverse. And the inverse is actually given. If you solve it, you will find the inverse. So it will be, if I'm not wrong, b minus ax plus a. So it's also continuous. Okay. So, and geometrically it should be clear, okay, that these two shapes are the same. And similarly, all open intervals of the real line are homomorphic. So first we prove that any open interval AB bounded is homomorphic to 0, 1 by the same homomorphism, actually, but we restrict its domain to the open interval. So the same formula works actually. But what is less trivial is why, for example, 0, 1 is homomorphic to R. Okay, so here we know that 0, 1 is homeomorphic to minus pi over 2 pi over 2. Just take a equal minus pi over 2 and b equal pi over 2. But we know that the tangent is a homeomorphism from minus pi over 2 pi over 2 into r. So therefore, we have a homeomorphism between 0, 1 and r. Okay, and now any semi-bounded interval a plus infinity is also homomorphic to r by this function len of x minus a. So in particular, if you put a equals 0, you get len of x. So len of x is a homomorphism. We didn't say that, but you understand that len of x is a homomorphism between the open interval 0 infinity into r, and its inverse is just the exponential. Okay. So all these intervals ab, a plus infinity, minus infinity a, because minus infinity a by symmetry actually it's homomorphic to the whole line. So all these open intervals, bounded or unbounded, are homomorphic together. Okay. So 0, 1, 0 infinity, minus infinity 0 are all homomorphic by very simple formulas. Okay. Now an ellipse, a circle and an ellipse are homomorphic. Intuitively, it should be clear because you should see how can we deform a circle and get an ellipse and then go back. And if you don't believe me, there are very simple formulas. If you consider the unit circle, x squared plus y squared equal 1, and you consider the ellipse of the form x squared over a squared plus y squared over b squared equal 1, then this transformation from R2 to R2 takes the unit circle into the ellipse. Okay, so what does it represent? It represents a stretching or contraction in the direction a by a factor a, and same thing in the direction of y. Okay, so two homomorphisms, if you like, or if a is less than 1, then this is a contraction. If a is bigger than 1, then this is a stretching. Okay, so it should be clear that a circle and an ellipse are topologically the same. They are homomorphic. They have the same form or the same shape, if you like. Think of in terms of geometric. Now, according to our general concept of homomorphism, it should be clear that rotations, translations, homomorphies, symmetries of the plane or three-dimensional space are all homomorphisms. Okay, because they are bijection, they are continuous, and their inverse is continuous. Okay, so a rotation is, of course, if whether it's a rotation with respect to in the plane or in the space with respect to an axis, it's a bijection, it's continuous, and we have simple formulas actually. It's just enough to have the angle of the rotation and the center, or the axis of the rotation and the angle. And then we have the matrix of rotation, if you like. So we have very simple formulas for the rotation. And the inverse rotation is the rotation with opposite angle or. So translations should be clear. X minus a becomes x plus a. Homomorphies just multiply by lambda. Symmetries with respect. Symmetry with respect to the center, to a center, is just a rotation of angle pi. With respect to an axis, you can find simple formulas actually, and you have also a matrix of symmetries. So all these things, if you should be clear that they are homomorphism. They conserve the shape of an object, even if they distort it a little bit. Now, rotation, translations, and symmetries are what we call isometries because they conserve the distances and the angles, of course. However, homomorphies can distort distances, but they conserve the angles. Okay, so these are really particular cases of our concept of a homomorphism, because a homomorphism can really do a lot of distortion to the geometric object. So this is why we started this course by saying that topology is a weird kind of geometry. Okay. Okay, another example, the punctured disk. So the unit disk without its center. Okay, so the equation is x squared plus y squared. It's the open disk from which I remove the center. So please draw a picture. So this punctured disk and the annulus. So this is the part of between two disks. Okay, so we are outside the unit disk and inside the disk of center of radius 2. Okay, so these two shapes are homomorphic, are the same actually. So we can, intuitively, we can distort this annulus to make it an annulus, and you can go back without breaking, without introducing any discontinuity. And once again, there are, if you don't believe your intuition, there are simple formulas. Okay, so here the coordinates of a point are xy. So we set capital X. This is just, so capital X is not a space here, just a couple. So maybe you can call it, you'll find other notation. Maybe you may write x1, x2, and here x, as you wish. But when I wrote this, I wrote capital X as a couple, xy. And now we define a function from R2 to R2. Okay, from R2 without 0 into R2, given by this formula. So it's x, the identity, plus x over its norm. Okay, so this is a map from R2 without 0 into R2. And if you reduce to the same denominator, you get norm of x plus 1 over, here we are taking the Euclidean norm. Okay, so now it's easy to check that f is a bijection from R2 without 0 into R2 without 0 as well. And if you solve the equation y equal f of x, you will find a simple formula for f minus 1. So it's just little algebra. And now it's clear from the forms that, of course, the norm is continuous. The ratio of two continuous is continuous, and this is just the identity. So it should be clear that f and f minus 1 are continuous actually from the plane without the origin into itself. So it's a homomorphism, a global homomorphism, that takes this punctured disk into this annulus. Okay, so check that. So sometimes it's not always necessary to write equations, but as a first encounter with the concept of homomorphism, you may have some doubts. Okay, so this is why we write equations. And it's important to write equations if you want to represent these transformations on a computer. If you want to do some animation, it's important to have formulas. So now, next example, a circle and the boundary of a square, or just a square, are homeomorphic. This is less clear because the square has 4 corners, whereas the circle has no corner. Okay, but so they are not diffeomorphic, but they are homeomorphic. So we can deform the circle into the square and vice versa. Okay. Actually, draw a picture and see what happens. Okay, so here once again, so for a topologist, a circle and the boundary of a square are the same shape. Okay, and here again, we can write equations, but to simplify a little bit the notation, I will just take the unit circle, and now we understand that all circles are the same. Okay, by a translation and the homotopy. Okay, so the circle of center 0 and radius 1 is homomorphic to the circle of any center and radius r, positive, of course. So for reference, we take the unit circle, and we take the rotated square that, so of equation absolute x plus absolute y equal 1. So this is, we already encountered this in chapter 1. This is like a diamond. So it connects the points 0, 1, 1, 0, minus 1, 0, and so on. Okay. So here there are simple equations that transform S1 into C. Okay, here are the equations. Actually, we have more than a homomorphism. We have a global homomorphism from R2 to R2 that takes the circle into the square, the interior of the circle, so the disk into the open square, and the complement of the disk into the complement of the square. So, so there are very simple formulas for this homomorphism from R2 to R2. So if it is from R2 to R2, it means that it has 2 variables and has 2 components. So the first component is just x absolute x, and the second component is y absolute y. And now it's clear that f is continuous because each component is continuous. Okay, and now if you solve the equation f of xy equal x prime y prime, okay, so this is just an algebraic system. If you solve it, you will find that f minus 1 of xy is g of the form g of x, g of y, where g actually is a function from R to R, which is radical x if x is non-negative, and minus radical x if x is less or equal than 0. So this map G is actually, can draw it. I encourage you to draw the graph of G. So it's radical x positive, and so it's symmetric with respect to the origin. Okay. So if you solve the equation f of xy equal x prime y prime, we'll find this formula. And now it's clear that f minus 1 is continuous as well. But we have to prove that f maps the circle into the square. Okay, so f of s1 equals c. How do I prove that? Double inclusion. So we take a point xy in the unit circle. So x squared plus y squared equal 1. And so therefore, but I can write x squared as absolute of x squared, or if you like, x times absolute x. Yeah, same thing actually, because this is just x squared. This is x squared is equal to this one. Okay, x times absolute x. So it's absolute x times absolute x, if you like. And this is the same thing. So, but x absolute x is just the first component of f. So actually, the x prime y prime, if you like, satisfy the equation of the square. Okay, so this means that f of xy belongs to the rotated square. Okay, so this proves that f maps S1 into C. For the converse, we take a point UV in C, and since f is a bijection, then UV is the image under f of some point xy. So xy is f minus 1 of UV, if you like. And now it's easy, because if absolute u plus absolute v is equal to 1, then it means that absolute of this plus absolute of this is equal to 1. And this precisely means that x squared plus y squared equal to 1. So xy is in unit circle. So this is just simple algebra. Okay, and you can prove actually more. It maps the open unit disk into the open square, and the exterior of the disk onto the exterior of the square. Okay, very simple. So sometimes a writing equation can be tedious. It's not always necessary to do that. Okay, so sometimes, and by the way, we accept pictures as a proof. In general, a picture is not a proof. But sometimes, when equations become tedious to write, we accept a picture, even in the exam. So because it tests your understanding. Okay. So when you draw me a picture, I see that you understood what you are talking about. Okay, now next example, the plane R2 and the complex plane are also homomorphic. Okay, so we equip R2 with the Euclidean distance that you know, and we equip the set of complex numbers by also the same distance. Then actually, the R2 is homomorphic to C. So we can identify R2 and C. We know that you can identify R2 and C algebraically. Okay, but here actually we can identify them topologically. So they have the same topological structure, and they both represent actually the plane. So it's not really important how do you note a point in the plane. You can denote it by a couple xy, or by a complex number x plus iy. Same thing actually. So the function, the homomorphism is just f of xy equal x plus iy. Right? So it's really very easy. It's a bijection, it's continuous, and its inverse is continuous as well. So, and moreover, actually, it's more than a homomorphism. It's an isometry because it conserves the distances. Okay, this is something really fundamental. Okay, now we move to a very important example. A circle with a point removed is homomorphic to the whole line. We do this via a very important map called the Stereographic Projection. And here it is. We take the unit circle S1 in the plane, so it's embedded in the plane, and we consider the north pole, capital N, of S1. Okay? And here is the picture. understand better. So this is the circle in green of center 0, 0 and radius 1. And this is the north pole of coordinates 0, 1. What does this stereographic projection do? So to each point M in this circle, it's represented in white, we join N to M. And the line joining N to M meets the x-axis, or the axis y equals 0, into a point M prime. Okay? So we may have this or this configuration, doesn't matter. So what is the geometric interpretation? What this stereographic projection is doing, it's projecting the circle without its north pole into the whole line. So imagine that you are opening the circle, because it's not, we removed a point. Okay, so it's like, yeah, it's a projection actually. So we are bending or flattening the circle without the point to get the whole line. Okay, now once again, so should be geometry, and of course it should be geometrically clear that this is actually a homomorphism, because we can go back. So going back involves wrapping the line into a circle without a point. But fortunately, there are very simple equations for this homeomorphism, and we shall discover them very easily. If the n has coordinate 0, 1, and m has coordinate xy, how to find the coordinates of the point m prime? It's very easy. We just write that the vector nm, or nm prime, is proportional to the vector nm. Okay, so there exists lambda. There exists lambda such that the vector nm prime is equal to lambda times nm. Now, we go back to school. The coordinates of this vector are x prime, so first component minus first component, so x prime minus 0. Second component minus second component, so 0 minus 1. And m has coordinates x minus 0 and y minus 1. So we have a system, actually, x prime equal lambda x and minus 1 equal lambda y minus 1. So lambda equal to 1 over 1 minus y. So if we replace this, we get that m prime has coordinates x over 1 minus y, and of course 0, because m prime lies on the x-axis. So that's it. So actually you have now a function from S1 without its north pole into R, that to each point xy, such that x squared plus y squared equal 1, its image is just x over 1 minus y. Of course, it's continuous because we removed the point. If xy is here, then y is different from 1, so we can divide by it. So this is, of course, something continuous. And if we solve for the inverse, the bijection, if we solve the equation f of xy equal t, we'll get x and y in terms of t. So, yeah, and I solved it here. So if t equal x over 1 minus y, then t times, so yeah, so t minus ty equal x, so t minus x equal ty. And yeah, so if you solve this, you'll get x equal 2t over t squared plus 1 and y equal t squared minus 1 over t plus 1. So this is simple school algebra. So of course, f minus 1 is a map from R, because t is a real number, and takes values in the circle. So it has two components. So it should be clear that it's a homomorphism according to our definition. Okay. Yeah. So this is the very important stereographic projection. Okay, we talked about the geometric interpretation. The first remark is that there's another way to see that a circle with a point removed is homomorphic to the real line, because we know that in the previous example, we showed that S1 without 1, 0 is homomorphic to the open interval 0 to pi. And 0 to pi is homomorphic with R. Therefore, R is homomorphic with a punctured circle. Now, of course, if you remove the north pole or the point to the right, it's the same thing, because these two are obtained by a rotation. So this is another way of showing that the whole line is homomorphic to a circle without a point, or just to an open interval. So all these shapes are the same. So for a topologist, open interval 0 to pi or 0, 1 or r or circle without a point is the same object. Okay, so, and however, now you may find in the literature a little different formula for f. What some people call stereographic projection is the projection of the circle without its north pole into the tangent opposite to the north pole. So here the north pole has coordinate 0, 2, for example. Or you may take the north pole equals 0, 1, but you project on the horizontal line y equal -1. You get a slightly different formula, but it's the same idea involved. Here, if you solve the equation, you get f of xy equal 2x over 2 minus 1. Same thing. So, but it's the same idea. Okay, and now we can generalize this to three-dimensional space. Instead of a circle, you can take a sphere. I will not draw a picture, you draw it. So once again, you take the two-dimensional unit sphere, and we remove from it the north pole of coordinates 0, 0, 1, and we do the same thing. Okay, so we connect a point M of the sphere, and this line will meet the plane z equals 0 at the point M prime. So once again, if you solve the equations, you will get this formula. So f of xyz is x over 1 minus z, first component. Second component, y over 1 minus z. And if you solve the equation x over 1 minus z, y over 1 minus z equal ts, you will find a formula for f minus 1. So it's this one. It's very close to the previous one. Okay, so this is what you call the stereographic projection. And of course, you may see variations. Instead of projecting on the z equals 0 plane, you can project on the plane z equal -1. You get slightly different formula, but it's the same idea. Okay, so this proves that the sphere without a point is homomorphic to R2. Okay, this is a really fundamental example. Okay, so R2, and even actually R2 is homomorphic actually to an open disk. Try to prove that. Okay, so open disk, R2, sphere without a point is the same thing. And you can generalize this to Rn. So we consider the n-dimensional sphere of equation x1 squared plus x2 squared plus etc. xn plus 1 squared equal 1. So here we cannot see any more the geometric significance, but we proceed as before. So instead of x over 1 minus z, y over 1 minus z, you have x1 over 1 minus the last component, x2 over 1 minus the last component, and so on. And of course, the last component is different from 1 because we removed the north pole, which of coordinates 0, 0, 0, etc., and the last component as well. So here again, if you solve the equation f of x1, x2, xn plus 1 equal t1, t2, tn, you'll get this formula. Okay, so here again, we have a homomorphism between the n-dimensional sphere with a point removed and the whole space Rn. Okay, so this concludes this lengthy list of, but it's really fundamental. So all these examples should be known. And the last concept that I shall cover in this video is the concept of embedding. Now, we don't always have homomorphisms from X into a space Y, but you may have something a little bit weaker. So we may have a homomorphism from a space X into its image. Okay, if this is the case, we say that F is an embedding from the space X into the space Y. Okay, and this means that according to our interpretation of the notion of homomorphism, a homomorphism is just two homomorphic spaces are just to represent two copies of the same object. Okay, so saying that X is embedded in Y means that we can put a copy of X inside Y. Okay, and now I'll give examples, of course. You can put a copy of the real line in R2 just by taking the line into the horizontal line of coordinates x0. Okay, so this is just. Okay, so this is of course an embedding. Of course, it's not a homomorphism because R and R2 are never homomorphic. Actually. So they are not homomorphic. I will tell you why later. Why R and R square are not homomorphic, but we can put a copy of R into R2. Okay. Okay, here's another embedding. We can put R into R2 by using another embedding. Instead of taking x0, we can take x cubed. Okay, so this means that if you plot the graph of x cubed, you'll find this curve. This curve actually is a deformation of R. It's a copy of R. Okay, so you have the straight line R. If you deform it by this embedding, we get precisely the graph. Okay, so this is another embedding. Less trivial embedding is the spiral. If you consider the function whose coordinates, so g of x, is e minus x cosine x, second component e minus x sine x. This is actually, if you plot it, you will find a spiral. As x tends to infinity, g tends to 0. Okay, so try to imagine a spiral. This spiral, this infinite spiral, actually is a copy of R. So here we see another interesting thing is that we have so many shapes homomorphic to R. Have the straight line R, we have the banded curve x cubed, we even may have an infinite spiral. So it's kind of wrapping, and of course we have the circle without a point. So all these shapes actually topologically are the same because we can go from one another without breaking them. Okay. And last example, trivial. 0,1 closed and 0,1 open are not homomorphic, and I will tell you why in the next chapter. But however, we can place a copy of course 0,1 is bigger than, so 0,1 closed is bigger than 0,1 open. However, we can place a copy of 0,1 inside 0,1. Just take g of x to be 1/3 plus 1 over 6x. Okay, what is the image of 0,1 under G? It's actually 1/3 plus 1 over 6. It's the interval, closed interval, 1/3 plus 1 over 6. This is a closed interval, smaller than the original one, but it's placed inside the second one. So this is another example of an embedding. Okay, we cannot put 0,1 directly inside open interval 0,1, but we can shrink it if you like, and then put this copy inside the open interval 0. So this is the meaning of embedding. So this concludes this video and concludes chapter 2, which is really, really fundamental in all topology. So please, if you didn't understand all the concepts, because I know that they are maybe a little hard, you can watch the video several times and you can read the lecture notes. So, but it's really something fundamental, and we always ask questions about homomorphisms. Okay. So thank you for attention. And in the next video, I'm going to solve some exercises of chapter 2.